Good morning, everyone. Spring has sprung, and it's actually really beautiful down here in lovely Las Cruces. And so, thanks for joining us this morning for this month's webinar. Today, we actually have a terrific trio presenting, including Dr. Pei Xu, Dr. Yanyan Zhang, and then Dr. Thiloka Edirisooriya. Dr. Xu, who everyone knows, is our wonderful research director at the consortium. She is also professor of civil engineering at New Mexico State University and a triple AS Leshner Fellow, and holds multiple endowed positions at NMSU. Dr. Zhang, who I think most everyone knows as well, is an associate professor of civil engineering at NMSU and really a key researcher in the consortium, specializing in ammonia recovery and toxicity assessment of treated produced water for reuse. And someone that not everyone has probably had the pleasure of meeting. Dr. Thiloka Edirisooriya is presenting today as well. She is a postdoc researcher in the civil engineering department at NMSU, focused on advanced water and wastewater treatment, including produced water management, desalination, and resource recovery. So those are my introductions for everyone this morning. I'm going to hand it over to Pei, Thiloka, and Yanyan, and the floor is yours.
Thank you so much, Zach, for the very nice introduction. And thank you, everyone, for attending the webinar. I'm very pleased to present the evaluation of removal efficiency and the toxicity study results of an integrated treatment train using the phase desalination and the seawater reverse osmosis as core desalination technologies. This is a collaboration between Texas Pacific Water Resources and the New Mexico State University. So in addition to Thiloka, Yanyan, and myself to present today, the co-authors of the study, including Adrian Lopez and Daniel Smith with Texas Pacific Water Resources, and also Dr. Huiyao Wang and Dr. Panhasa Senanayake and Pumi Veerasinghe, and also Dr. Himali at New Mexico State University. Next slide, please. So, Permian Basin is the most active basin for oil production in the United States. And at the same time, a large amount of produced water is produced. So produced water disposal has increased in the Permian Basin from about 0.9 billion barrels in 2010 to over 5 billion barrels since 2025. About 85% of the produced water is managed by underground injection through the saltwater disposal wells or through the wells for enhanced oil recovery. Produced water disposal has become a major challenge in the Permian Basin as well as in the United States due to the declining injection capacity, the increasing seismic activity as shown in the two graphs on the right, and this has increased the level of regulatory oversight. But on the other hand, if we can treat and reuse the produced water, this will mitigate the environmental impacts through the underground injection. Also, it can provide an alternative water supply. So the next slide will show that the water chemistry in the produced water, because if we want to treat and reuse this water, we really need to understand what are in the produced water, and we need to evaluate the treatment efficiency to ensure that the treated produced water could meet the fit for purpose water quality requirements. So produced water has a complex chemistry. It has all kinds of constituents in the water, including the suspended particles and the salts, ammonia, heavy metals, and naturally occurring radionuclides, all in the grades, volatile and semi-volatile organic compounds, and other trace compounds, and also including the chemical additives during the hydraulic fracturing. And if you see the table on the left, It shows the bulk water quality in the Permian Basin. The average TDS is about 130 grams per liter, and with the range from 100 grams to over 200 grams per liter. The total organic carbon average is about 100 milligram per liter, but it can up to 250 milligram per liter that we have monitored. The pH is 0.6, but it can vary between 3.9 to over 8. And also the total suspended solids concentration is about 340, and it can vary between 85 to almost 800 milligram per liter. So we can see that the produced water in the Permian Basin is hypersaline. We cannot use the conventional reverse osmosis technologies such as the seawater reverse osmosis directly to treat the Permian Basin produced water because it needs very high hydraulic pressure due to the high osmotic pressure. So we need to use innovative technologies or use the thermal desalination. And also due to the complex water chemistry, then we need robust pretreatment because even though the Permian Basin produced water is dominated by sodium chloride because this is ancient ocean water, but it also has different types of constituents that can cause scaling and fouling. So for the safe reuse of the treated produced water, we need a multi-stage integrated treatment train, including the pre-treatment, desalination processes, and also post-treatment to polish the water quality. We need to have a comprehensive characterization of the produced water, including targeted analysis, non-targeted analysis, and the toxicity studies. And also we need a very close monitoring of the water quality. And the next slide will show us the integrated treatment train. And this graph, it shows the different options for the pre-treatment, desalination, and post-treatment. So the goal of the pretreatment is to remove suspended particles, oil grays, and other constituents that can cause the problems of the downstream treatment processes or the beneficial use of that water. So the pretreatment may include the dissolved air flotation, coagulation, flocculation, that could be chemical added or electrical driven, and the sedimentation, filtration, and it may also involve the biological treatment and the oxidation processes to remove, for example, the iron and also the hydrogen sulfide and also disinfect that water. The common two desalination technologies are membrane-based, such as using the multi-stage nanofiltration and reverse osmosis, or using the phase desalination followed by reverse osmosis. That is the technology developed by the Texas Pacific Water Resources, and also thermal-based desalination technologies. And after that, post-treatment is very critical to further polish the desalinated water and remove any residual contaminants of concern. We can use advanced oxidation, ion change, and the selective resins to remove ammonia, and the adsorption using the granular activated carbon to remove residual organics. And we can even use a secondary desalination process, such as if boron concentration is high, we may use a secondary reverse osmosis. And then we can also use other biological and natural-based finishing steps, such as the wetland. And the next slide shows that the overview of the studies. We collaborate with Texas Pacific Water Resources. And the raw produced water was sourced from a saltwater disposal site in Midland, Texas. And then this study was conducted for almost 10 months, and it treated 30 to 45 barrels of the produced water per day in a batch operation. Then during this study, we monitored the up to 448 constituents through 6 sampling events through the 10 months pilot testing project, including the bulk water quality parameters, salts, and the radionuclides, organics, and trace organic compounds. And also, we conducted the risk assessment that we are going to talk about today. And also, during the webinar next month in June, Dr. Simon Schramm and also Dr. William Hahoreksa will talk about the non-target analysis of those samples. In addition to these water quality characterization, and Texas Pacific Water Resources also conducted a 9 months greenhouse study using the treated produced water of different salinities to irrigate the native plants and the alfalfa. The results of the irrigation experiments have been presented in the consortium webinar on December 17th, 2025 by Adrian Lopez and also by Dr. Panhasa Senanayaka. And currently, we have already published 3 papers, peer-reviewed publications in the Science of the Total Environment, Separation and Purification Technologies, and also in the journal Desalination. So all these papers have already been posted in the consortium website. We have other papers, and we highly encourage you, if you want to know the details of the studies, please go to the consortium website and you can download those papers. After this, I'm going to hand this over to Thiloka to talk about the details of technology assessment.
Thank you, Dr. Xu. As Dr. Xu mentioned, Texas Pacific developed this treatment technology where they have tested the freeze desalination and reverse osmosis treatment train to treat the produced water to apply in the reuse application, and we analyze the separation performance of this integrated treatment train. So let me explain about the treatment train first. So this treatment train consists of 6 stages. So first they have pre-treatment process, the first 2 stages. So first one is the oxidation and physical separation. During this oxidation and physical separation process, they were targeted to remove suspended solids and oil and hydrogen sulfide from the produced water streams. And as the second stage, they have additional pretreatment stage with coagulation, flocculation, and filtration. There also they targeted to remove the suspended solids, hydrocarbons, and also some dissolved gases from the produced water stream. So as their third stage following the pretreatment, they have this freeze desalination system where they targeted to remove dissolved solids from the pretreated waste stream. So most of the dissolved solids are removed by reducing the waste load to the preceding stages. So after the freeze desalination stage, the treated water will go through a GAC filter where it was filtered through anionic charge glass sand media filter and granular activated carbon filter. So this stage is used to reduce the organic and dissolved solid load to the preceding stage, which is the seawater reverse osmosis. So the fifth stage of treatment is seawater reverse osmosis, where most of the dissolved solids and organics are removed during the seawater reverse osmosis process. After the seawater RO process, they have GAC and disinfection. GAC filtration is to further polish the treated seawater RO permeate in case of residual organics and inorganic compounds, and also to remove microorganisms that remain in the treated seawater RO permeate. So, considering this treatment system, as Dr. Xu mentioned, this system was operated for around 10-month period from November 2023 to August 2024. And during this operating period, there were 6 major sampling events were conducted and evaluated extensive list of analytes as shown in this table. So up to 448 analytes were analyzed, and the water quality at each sampling points at each different sampling events were analyzed during this analysis process that we conducted. So the concentrations of all of these analytes and with their statistical indicators like average standard deviation and the first and third quartiles were calculated, and also the removal efficiency and the variability of the water quality was evaluated and calculated, and these data are presented in our publications. So if you like to see the more details about these analyses and also the water quality variations, you can check these publications. The supportive information include all the extensive list of analytes and the parameter variations. So moving on to the next slide, let's talk more about the bulk produced water quality and desalination throughout the stages. So here we can see the bulk water quality parameters like electrical conductivity, total suspended solids, total dissolved solids, total organic carbons, and alkalinity and ammonia. So here we could see that pretreatment mainly reduces the suspended solids while freeze desalination step drives bulk desalination, and then the GAC and seawater RO provides the final polishing of the water. And in this case, we could see that overall salinity or the salinity related parameters were removed most effectively with electrical conductivity and total dissolved solid removal reaching over 99% after the seawater RO treatment. And when considering the overall treatment, it confirmed that the combined the process or the integrated treatment system is highly effective for hypersaline produced water desalination. And when it comes to organic and alkalinity indicators, they were also substantially reduced throughout this treatment system. And when it comes to the ammonia reduction, we could see that after seawater RO treatment, 99.4% of ammonia removal was observed, and also that the permeate exhibit the average concentration of 3.2 milligrams per liter of ammonia concentration, and it was further reduced to 2.3 milligrams per liter after the polishing stage, after the post-treatment with GAC filtration. And moving on to the concentration of the variation of the cations in the produced water and in the treatment stages. So concentrations in the raw produced water span multiple orders of magnitude of major ions, considering as sodium, calcium, and magnesium dominating in the mass load in the raw produced water. And when it comes to the pre-treatment, it yields modest and analyte-dependent reductions, largely benefit typically for particulate associated total recoverable fractions rather than the dissolved organic, dissolved species. And when it moved into the freeze desalination stage, it provided a clear step change reduction of these cations. Many constituents in the cations, but the residual dissolved ions remain for several species. But with the GAC and seawater RO treatment process, it remove most of these cations to trace or near below detection limit levels for most of the analytes. And we can see that overall removal efficiencies are clustering near above 95%, and it varies within the 95 to 100% range. So it indicates that this integrated treatment train achieved over 99% removal of the evaluated inorganic chemicals, as we can see in this figure. So with that, we move on to the anions and radionuclides removal. So in a similar trend, we can see that pre-treatment shows limited removal for most of the anions that we considered. But when it comes to the freeze desalination, it was the key anion as well as radionuclide removal step in this treatment trend. So it removes the bromides, chlorides, sulfates, and fluorides as well as the phosphates. So over 90% removal efficiency for bromides and over 80% removal efficiency for chlorides were observed in this treatment train after the freeze desalination. But after GAC plus seawater RO treatment, it could polish this water by removing over 95% of overall removal of these analytes. So most of the dominant anions like bromide, chloride, and sulfates, they were removed within the range of 95 to 100% after the seawater RO treatment process. When it comes to the radionuclides, we can see that concentrations of the radionuclides drop by 3 orders of magnitude by removing over 99% of the radionuclides removal after the seawater RO treatment process. And also with the GAC polishing stage, the removal efficiencies were increased by eliminating almost all the radionuclides into trace concentrations. So, in that discussion about the inorganics, let's move on to the bulk organics characterizations in the raw produced water. So, we have conducted comprehensive analysis to quantify total organic carbons, hexane extractable materials, as well as total petroleum hydrocarbons and various petroleum hydrocarbon fractions including gasoline range organics, diesel range organics, and oil range organics in the collected samples. So there we could see that average total organic carbon concentration was around 32 milligrams per liter, and it has, so we fraction them and see what are the fractions of VOCs, volatile organic carbons, semi-volatile organic carbons, and also the hexane extractable materials represented by these TOC concentrations. So there we could see that 30 during this in these TOC concentrations, 63.5% is unresolved or undetected organic carbons, but we fractionize the other SVOCs, VOCs in this TOC concentration. So SVOCs contributes to 18% and HEM or the hexane extractable materials represented by 11.4% and VOCs were represented by around 7% by the TOC equivalent mass. So within this distribution, we could see that TPH is account for 3.36 milligrams per liter, and it is distributed across different hydrocarbon ranges, as I mentioned before. So, understanding about these raw produced water organic compositions, we move forward with analyzing the bulk organic parameters and their concentration and removal efficiency variation throughout the treatment stages. So there we could see that average TOC removal in the seawater RO permeate was around 93%, and over 99% of hexane extractable materials were removed after the seawater RO treatment. And also, over 89% of total petroleum hydrocarbons were removed, and over 71% of average total organic halides removal was achieved after the seawater RO treatment. And with the GAC post-treatment, following the freeze desalination, GAC seawater RO, and the GAC treatment, reduced TOC to 1.52 milligrams per liter, indicating a significant organic reduction after following the GAC post-treatment. So, with that understanding about the bulk organic parameters, we analyze more and in-depth characterization of volatile organic carbons. There we consider total of 94 volatile organic compounds, and they were quantitatively analyzed across these samples, and then we assess the efficacy of the treatment process. So, among these analyzed volatile organic carbons, 14 of volatile organic carbons were detected at least once across these considered samples. So, the majority of the VOCs were detected in raw produced water as represented in this figure, and they were removed eventually with the pre-treatment and the freeze desalination, and also with the seawater RO and the GAC treatment. So, as I mentioned, majority was in the raw produced water, and 8 of these 14 detected VOCs were eliminated below the method detection limit by the pre-treatment process. And then also, freeze desalination is acted as important intermediate barrier for both VOCs and also the semi-volatile organic removal. And in addition, the addition of the GAC treatment as the post-treatment to the seawater RO, it effectively polished the treated water by reducing almost all the tested VOCs below the method detection limit. But and also the trace concentrations, the observed concentrations were trace concentrations near the method detection limit, and also there were minor variations in the dilution factors or the metric composition, and also the coelution behavior, which can affect the detection of these compounds throughout the treatment train. And with that understanding, we after the additional GAC treatment, we can see in this table most of the detected compound, even after seawater RO permeates, were eliminated below detection limits. So none of the detected compounds were observed after the polishing stage with the GAC treatment. So with that, we'll move on to the semi-volatile organic carbon removal. So there in the raw produced water stream and across the samples, we analyzed total of 138 SVOCs in raw produced water, and 111 SWRCs in pre-treated and freeze desalination treated water, and also 142 SWRCs in the GAC and seawater RO treated water. So, and among them, the maximum number of detected SVOCs in the pre-treated produced water, freeze desalination treated water, and GAC and seawater RO permeate was 11, 6, and 3 respectively. As we can see, the number of detected compounds were reduced when proceeding with the treatment stages. And it demonstrates that there is progressive elimination of these compounds through the treatment stages. And after the GAC and seawater RO permeate, there were trace concentrations of the analytes like 2-methylphenol and 2,4-methylphenol, but they were also eliminated, as we can see in this table after the GAC treatment, where all of the concentrations were reduced below the method detection limit. So it shows that the seawater RO permeate with GAC has shown the all tested semi-volatile organic carbons below the method detection limit. And also, the comprehensive organic analysis consists of 19 SVOC explosives and also 22 organochlorine pesticides and 11 chlorinated herbicides, 7 polychlorinated biphenyls and 15 organic acids, 17 dioxins, and 8 compounds in other categories. So among these categories, we did not observe PCBs or dioxins in the collected samples. And for semi-volatile organic explosives, 1 organochlorine pesticide and 1 chlorinated herbicide and 1 organic acid were identified across the analyzed samples. So, but we can see that the treatment process effectively reduced or the eliminated all of these detected compounds to below method detection limits. So when it comes to the methylene blue active substance MBAS, they were also effectively reduced by over 86% efficiency, and it demonstrates the efficacy in mitigating the surfactant related contaminants from the uh, removal of these MBAS throughout the proceeding with the treatment stages. So, following the similar trend, we can see that the following GAC treatment has eliminated all of these contaminants, the concentrations to below method detection limits. So, none of the compounds were identified after the polishing stage with GAC treatment. Let's talk about the PFAS, removal of the PFAS throughout the treatment train. So PFAS occurrence was minimal and it is compound specific, but we have analyzed 34 PFAS compounds across these samples. From among them, 4 of them were detected in the raw produced water, and also, after pre-treatment, there was 1 detected at trace concentrations and freeze desalination water, and also in the GAC and seawater RO permeate. But with the GAC post-treatment, it eliminates all tested PFAS compounds below the method reporting limits, including the PFOS that we were detected in the seawater RO permeate. So, with that understanding about the removal efficiencies and concentration variations, we conducted the organic removal sustainability by correlating the TOC concentrations with the number of analyzed organics and also relate it with the number of detected organics in the seawater RO permeate and the GAC post-treated sample. So there we could see that the lowest and the fewest detected organics were observed in the August 2024 sample, and it has the TOC concentration lower into 0.2 milligrams per liter, and there were only two detected organics showing, and it shows the strong treatment performance during the that specific sampling event. And when it comes to the June 2024 sample, that sample showed the highest total organic carbon concentration with around 4 milligram per liter, and it has the largest analytical screening scope, where we analyzed 332 analytes, and among them, 5 of the organics were detected. And these results show that integrated treatment train it produced consistently low residual organic occurrence. And also, if you see the August 2024 sample, it has the lowest TOC concentration and it has the significant screening scope with 310 analytes, but none of the organics were detected after the GAC treatment. So it emphasized the final GAC polishing step, and also it has eliminated all detected organic compounds in the targeted analysis. So with that understanding, we try to build this principal component analysis to relate the to understand the mechanism, removal mechanisms based on the physiochemical properties of the organic compounds. Here we consider about the parameters like melting point, water solubility, molecular weight, and also the Henry's log constant. And we try to relate the removal efficiency with these parameters and try to understand the mechanism, the removal mechanism based on these parameters. So for the GAC and seawater RO stage, the first three components captured the most of the variance with PC1 reflecting the size and lipophilicity versus the solubility, and PC2 representing the volatility. So in contrast to freeze desalination process, removal after GAC and seawater RO process was mainly associated with the principal component 3. And also the principal component analysis show that there is consistent descriptor grouping across the both stages of freeze desalination system as well as the GAC and seawater RO system. And from this, we could see that the removal behavior in the integrated system is mainly compound specific, and it was not fully explained by the selected molecular descriptors or the parameters alone. So from this, I will hand over to Dr. Zhang to talk about the toxicity studies.
Thank you, Thiloka. Good morning, everyone. So I'm going to present our toxicity result for the treated produced water. So we did two types of study. So the first one is the cytotoxicity study. So we used like 4 types of human cell line to see whether the treated produced water will affect the viability of human cell lines. So those 4 human cell line, including the MCF7, breast cancer cell line, HEK293, kidney cell line, HEPG2, liver cell line, and A549, which is like lung cell lines. So in this case, we can cover the cell lines from the major organ of the human. So we use like 2 types of viability tests. So the first one is MTT assay. which quantify the one type of enzyme activity, which is oxireductase enzyme activity. So the second type of viability test is by using cell title glue tool, which is the assays by quantify the ATP level of the cells. So those two type of viability assay give us the consistent result. For the untreated or raw produced water, so we have almost no survival cells. So I mean although the raw produced water has a lot of organic compounds, but the cytotoxicity are mainly caused by the high concentration of salts and ammonia. So in the produced water. So although the raw produced water had something like formaldehyde, or other compounds present, however, they are well below the reported cytotoxicity levels. So after freeze desalination process, the cytotoxicity still maintain low. So still after a freeze desalination process, we have around 27 gram per liter of salts. And also we have 123 milligram per liter of ammonia. So both constituents are affecting the cell viability. Although still we have the organic compounds formaldehyde below the reported cytotoxicity endpoint. However, those formaldehyde exceed the EPA regional screening level. So that means we still need to do the post-treatment, get rid of organic compounds as well. So after the granular active carbon and the seawater RO treatment, we see the cell viability went back to 100% relative to the control. So that means the post-treatment GAC and the seawater RO already remove all the compounds that are causing the cytotoxicity. So after the GAC and the SWRO process, so although we didn't really see the cytotoxicity, but we did see one compound, which is acrylamide, it's over the EPA regional screening level. So that means a long-term exposure could cause some health problem. So the good thing is the last step, the second GAC step, get rid of that a chemical. So acrylamide. So in this case, so all those detected organic are removed, so which ensure the human health. So next slide, please. So the second step study is a standard whole effluent toxicity assay. We send the sample to the a commercial lab, European, so did the whole effluent toxicity study. So we use 3 types of aquatic organism, so including the water flea, Sidubian, Fehemino, and also freshwater algae. So we did both chronic acute study and a chronic study. So for acute study, as you can see, so we did a 2-day survival for both water flea and Fehemino. For the chronic study, we did either the 6-day for the water flea and 7 days for the Fehemino. So that's survival. And also we have more endpoint including the neonate production. Then that's the indicator for the reproduction of the water flea. So we have the number how many neonate produced by each male adult. As you can see, whether the percentage of the treated produced water, I would say this is a produced water after the GAC and the seawater RO effluent. So all of them had the similar number with control. And for the Fehemino, so we also had the 7-day weight growth. We also see there is no difference between the 100% of GAC, seawater RO effluent, and the control. So we also used the freshwater algae did chronic study. We observed the growth of the algae to verify another type of chronic toxicity. But anyway, as you can see from all those plot, so all the treated water made the acute and chronic low risk benchmark in the test of significant toxicity analysis. So that means So all of them like giving you like 100 no observed effect concentration at 100% of the treated produced water. So that means we even without dilution, so this water won't cause the toxicity. So all the organic, although we have some detected organic compounds in the GAC and the like seawater, our effluent permit. So however, they are in very low level, they won't like cause any like acute and chronic toxicity. And also we also test the like the wet toxicity result like by using the final effluent. That means like we have another secondary like granular active carbon. We get the same result, exactly same result. So no like toxicity was observed like for all the like aquatic organism. So, but I just want to mention, so we still see some like detected ammonia in the final effluent. So we see like 2.3 milligram per liter of ammonia in the final treated water. So which exceed so the recommended aquatic life criteria for an average 30-day exposure, which is should be like 1.9 milligram per liter. So that's why additional step like by using either the like a zeolite or ion exchange to get rid of the residual ammonia is recommended. I will give the floor back to Thiloka.
Thank you, Dr. Shang.
Thank you.
With that understanding about the risk and toxicology analysis, we compare these treated produced water quality with reference standards. And I have to mention that we have extensive and in-depth literature review that we consider most of the standards for different reuse types other than that we presented here. So this is an example that we compare the seawater RO permeate quality and also the treated produced water quality after polishing stage with GAC treatment and compare it with the existing reference standards for land application, irrigation, and also we presented here the drinking water secondary and primary MCLs from US EPA. So we try to compare these water qualities with these reference standards. So what we see was that here with the post-treatment, it was consistent and comply with most all of these regulatory criteria, and it emphasized the importance of the post-treatment for consistent with the regulatory compliance. And when it comes to the multi-stage system, it produce water within the relevant criteria. Fluctuations in the raw produced water quality could occasionally push the seawater RO permeate close or above the certain thresholds, but it can be we can reinforce the treatment stages with final polishing stages. And when it comes to the land application and irrigation, most of the inorganic constituents met the target criteria, and post-treatment further improved the key constituents such as boron and chloride. And also, in particular, for the post-treated boron, here we can see the concentration of 0.37 milligrams per liter. It met the irrigation guidance, which was 0.75 milligrams per liter. So, and also it met the long-term thresholds for sensitive crops as well. And also with the low sodium and chloride in the post-treated water support the irrigation suitability. Also, the elevated levels of these ions can feasibly degrade the soil structure and infiltration, and also it can increase the salinization risk. And when it comes to the Surface discharge, as Dr. Zhang mentioned, surface water discharge remains more challenging because the ammonia is the key limiting constituents. The ammonical nitrogen concentration exceeded the aquatic life uh, quality criteria, indicating that the additional ammonia polishing, like zeolite or ion exchange, is needed for long-term discharge applications. And even so, wet testing showed no measurable toxicity for the treated produced water after ammonia removal with zeolite, indicating that the integrated system is effective in reducing ecological risk, and it supports the reuse feasibility. So, with that, I will conclude the today's webinar. So with this pilot scale treatment train, it shows that effectively treated highly saline produced water and composition for the compositionally complex produced water. And this integrated pre-treatment, freeze desalination, granule activated carbon, seawater RO, and granule activated carbon again approach can substantially improve the water quality for beneficial reuse applications. And this combined process achieved over 95% removal for most of the physiochemical parameters, and also the downstream polishing steps improve the overall stability and the final water quality despite the highly variable raw produced water quality. And the organic removal was strong across the multi-stage treatment process with high removal of total organic carbons, total petroleum hydrocarbons, as well as total organic halides. And the toxicity testing proved and it support the reuse feasibility, as well as the wet test shows no acute or chronic toxicity for the post-treated water tested in aquatic organisms. Also, the final treated water met the existing regulatory benchmark and the water quality requirements for land application, irrigation, and drinking water based reference criteria. So, with that, I would like to acknowledge the New Mexico Produced Water Research Consortium, as well as New Mexico Higher Education Department's RPSP program for supporting this study, and also for the Texas Pacific Water Resources for collaborating with us and for sharing data, and also all the hardworking NMSU research team. I would like to acknowledge their effort here. And if you have questions, we would like to contact, and these are our contact details. And with that, thank you so much. And we would like to take any questions from the audience. Thank you.
All right, come on, folks, don't be shy. What questions do we have? Maybe I'll kick us off and start us off with one. So for the trio here, it looked like the ammonia was a little bit elevated relative to some of the endpoints, but we still didn't see any of the acute toxicity. Do you think that additional post-treatment would be required to get the ammonia down from 2.3 to a lower level?
I can start I feel it really depends on the end yields. So if we do the surface water discharge, so we should meet the recommended aquatic life criteria 1.9 milligram per liter. So but if we do the agricultural irrigation, I don't feel that's an issue.
So maybe I can help to answer some questions in the chat box. I think Michael and Laura both ask about the energy requirement for the technologies. I know that Texas Pacific Water Resources is doing the energy consumption, but for these for this study, currently we focus on the fully characterization of the produced water and removal efficiency through the treatment trains. So we did not include the energy consumption, but I know we talked to Texas Pacific Water Resources that are working on it. So will the slides available and the webinar will be posted on the consortium's website and also on the YouTube. I know Zach and the team is working on it, so it will be available. Dave asked the question, the water recovery of the treatment train, how much waste was generated? I think we presented the recovery in the paper, but I could not remember now. Thiloka, do you remember the water recovery? So, Dave, if I'm not sure I remember the recovery date now. We will get back to you on that one. So Kurt's question is great. Is there a cost per barrel estimate for each stage of this process? So again, the study we are currently doing is on the characterization of the produced water, and we did not calculate the cost. But again, Texas Pacific Water Resources, they may have some cost information. So in addition to this, we have in parallel effort is to do a real world TEA on different treatment processes, membrane-based and the thermal-based. That is ongoing. It includes the pre-treatment desalination technologies and the post-treatment. And hopefully in the next few months, we will complete that study and then can share with the consortium members. And also we are preparing the publications, and Dr. Zach Stahl is also involved in the TEA. We are working with industrial partners and vendors for the TEA analysis. Okay, Yan Yan, thank you. Water recovery is 55%.
Yeah.
Okay. Okay. Are there any other questions?
Hey, there are a ton of questions in the chat still.
Okay, yeah. I think Norman asked the question, where does ammonia come from? Is it part of the water in the formation, or is it one of the chemicals injected downhole to help recover the oil? Ammonia comes from the natural formation water because it can come from the biomass to generate the petroleum hydrocarbons, because in the ancient time, the biomass may include the proteins or the nitrogen bearing organics. Eventually, they could be degraded over millions of years, become ammonia. Do we know what form of energy was being used in the treatment? Diesel, natural gas? I know you don't have quantification yet, just wondering which form of energy was used. I think it is electricity, but I'm not too sure. Sarah, I'm sorry. I do not have a good answer. Thiloka, do you remember?
Yeah, it could be probably electricity, but we have to check with Adrian.
Right. Yeah. Thank you, Thiloka. Any thought about the norm in the water? So for the Permian Basin, we detected high gross alpha, gross beta, and radium 226 and 228. So Thiloka has the data after the treatment, and they were removed to very low levels. So Thiloka, do you want to comment on that one?
Yes, Dr. Shu. In the raw produced water, we could see that gross alpha around 1800, and it was dropped to 4.7 picocuries per liter after the treatment, and gross beta was above 1000 picocuries per liter, and it was also removed to 3.6 picocuries per liter after the removal. And we observed radium 228 and 226 with concentrations around 200 picocuries per liter. And they were dropped below 1, like 0.19 and 0.73 picocuries per liter after the treatment.
All right. Any other questions? I think we have answered all the questions in the chat box. Oh, Philippe has a comment. Was this a 2-year analysis effort? The samples were taken 2 years ago. Yeah. So Philippe, the study was between November 2023 to August 2024, and it takes more time for implementing the pilot testing project. As you know, you are also doing the pilot study, and also it takes time for us to complete all the analysis and also publish the papers. And actually, for next consortium webinar in June, and Dr. Simon Sham and also William will present non-target analysis, and the manuscripts are under preparation.
And I think Laura still had a clarifying question for you in the chat.
Okay.
She was
So
just, go
to recap, the water recovery of 55% was for what level TDS? So Laura, I think for the Texas-Pacific water resources, their TDS has some variability, but on average, it is 130 grams per liter as a feed, and for the product water, it is between about 500 to about 120 milligram per liter in the product water or in the treated desalinated water. Laura, do I
Thank you,
answer
Pei.
your question? Okay.
Yes, ma'am. Thank you. I'm curious, while we're live and conversing, there was some discussion on LinkedIn about TCEQ feeling they didn't have a lot of information, qualitative information about the water quality and our ability to treat it. Didn't know if TCEQ had a representative on this call, or we needed to make this information available to them.
Yeah, Laura, that sounds a great idea. And then we will share these publications with the regulatory agencies.
Wonderful. Great progress, everybody. Beautiful work.
Yeah. Thank you, Laura. Okay. Sounds like we do not have any further questions. If there are no more questions, thank you so much, everyone, for attending our webinars. And then thank you, Yan and Thiloka, for the great presentation. And then thank Zach for hosting the webinar.
Thank you.
Thank you, everyone.
Thank you very much.
Thank you, everyone. Bye.
Bye.